Double displacement reactions. This type of reactions characterize themselves by the presence of two ionic substances on the reactant side. In the process of the reaction, the ions are actually scrambled. And one way to look at it is that you are swapping cations with each other, or you could also look at it from the point of view of the anions. The anions are being swapped. But one interesting thing that distinguishes double displacement reactions from single displacement reactions is that there is no charge change at all. Whatever the charge of the cations are to begin with remains the same on the left side and right sides of the equations. And the same thing is true for the anions. The anions don't change charge either. All that's happening is that you're swapping partners. Let me show you an example. If we have sodium phosphate being mixed with calcium chloride, we can determine the products of this reaction by the premise that the cations are going to be swapping places. All right, now in this particular problem, I'm going the extra mile of giving you the names of the molecules as opposed to the structures, just to facilitate your practice of nomenclature. All right, so sodium phosphate, we start with that. We have Na for sodium, and phosphate we have PO4. Calcium we have Ca, and chloride we have ClO2. Hopefully you do remember that from your nomenclature. But in addition to that, you also have to come up with the charges. +1 for sodium, 2+ for calcium based on their location in the periodic table. The charge of phosphate as well as the charge for chloride can be determined using group number -8. Specifically the group number of phosphorus and the group number of chlorine. Alright, with those charges, you can cross multiply to get the proportions. Bring the 3 in front of the sodium, bring the 1 in front of the phosphate, bring the 2 in front of the chloride, bring the 1 in front of the calcium to get the following. Okay, that's how you would determine the reactants. Now, what's going to happen is that because you do have an ionic substance reacting with another one, you're going to have to swap the cations. Alright, so what that really means is that you are trading places. Now, one way to do it is to literally write, you start with sodium on the right side and you start with calcium afterwards. Write sodium first, write calcium later, in the same order, and simply swap their partners. Phosphate used to be with sodium, now it will be with calcium. Chloride used to be with calcium, now it is with sodium. But once again, all that I'm bringing over is the unit with its charge. So chloride, 2 oxygens, 1 minus charge. Phosphate, 4 oxygens, 3 minus charge. I am not bringing the subscripts outside of the parentheses or in front of the metals themselves. That does not come over. We're going to let the charges tell us the proportions. Specifically, we're going to cross multiply. +1 goes in front of the ClO2. The 1 of chloride goes in front of sodium. The 2 of calcium goes in front of phosphate. The 3 of phosphate goes in front of calcium. So what you got to end up with is the formula right here. Notice that we have parentheses in front of PO4 because we have the subscript 2 arising from the charge of the calcium. Okay, so now we have the proper proportions. We have determined the products of this double displacement reaction by looking at the charges of the cations and the anions alike and simply swapping them. One mistake that does happen, and people make it, and hopefully you won't, is to accidentally give me a product where you have mixed cations together or anions together. If you ever do that, you will get marked down because that will be totally wrong. In water, situations like that are usually not ever experienced, and even if you do try to do something like that experimentally, you'll end up just reacting away your neutral metals with water. So make sure that your cation is mixed with an anion on both sides of the equation. Okay. All right, now in terms of balancing this, I'm going to show you a little trick. You do not need to do this necessarily, but the emphasis is on the fact that the phosphate and the chloride are not changing at all going from left side to right side of the equation. You have PO4 on the left side, you have PO4 on the right side. You have ClO2 on the left side, you have ClO2 on the right side. So you could actually treat them as units. And if you will, you could even replace PO4 with a big X and ClO2 with a big Y, symbolically, okay? But still the same thing. The premise is that ClO2 and PO4 are nothing more than units. So here you can just use the units to balance the equation. You have 3 sodiums on the left side, you only have 1 on the right side, you need to balance that. You have 2 Ys on the left side, you only have 1 on the right side, you need to balance that. Now, looking at this, we can see that X, we have 2 X's right here on the right side, but we only have 1 on the left side. So the first thing to probably be done is take care of that. Alright, so we are going to balance the X first. And notice that the moment that happens, we have changed the amount of sodiums. Now we have 6 sodiums on the left side of the equation, meaning that we need to add a 6 in front of sodium Y. That also changes the amount of Y. We have 6 Ys right now, but we only have 2 on the left side, so we need to multiply calcium chloride by 3. And that, of course, changes the amount of calcium. We have 3 on the left side, and we have 3 on the right side. So now that's balanced. Now, needless to say, if you decide to substitute your polyatomics with subscripts, or rather symbols, don't forget at the end to change the symbols back to the actual identities, the phosphates and the chlorides. If you don't want to use the symbols to balance the polyatomics, don't do that. That's totally optional. But do treat the polyatomics as units, because in a double displacement reaction, they will not change going from left to the right side of the equations, but they will be scrambled.